And if you have an extra couple of minutes, find the rest of the homework that's sort of in that bin, or that rolly cart over there. So, welcome back to class. How'd the homework go? Some homework? How'd it go? Went okay? Okay. Not exuberant either way. So, all right. So let's move on with chapter 12. We've been talking about screening designs. And again, the idea in screening designs is we cannot complete a full factorial. So we're doing fewer runs. And there's a price to pay in doing fewer runs. And that price that we pay is confounding. So that means the data are more difficult to interpret than in a full factorial. So when we calculate a number for an effect, that's not just a one thing. It's due to either two things together or four things together or eight things together, depending on how fractionated that design is. So what we've done up until now is we've talked about how to determine the confounding, right, with our defining relations, and how to generate a design. You do a base design in the full factorial, then you add factors, so those are added factors. Like this, you assign x4 to some interaction, you assign x5 to another interaction. That would be in this example where we have a 2 to the 3 base design of 8 runs, and then we add 2 more factors to it. So we're studying 5 factors in 8 runs. And we can come up with the defining relation, and from that we can figure out what that confounding is. So here it's a 1/4 fractional factorial, which means the confounding happens in groups of 4, and we can figure that out. So we talked a little bit about there's an appendix. I believe it's on Blackboard. If it's not, let me know. I'll get it to you, and you can print that out. And so there's this appendix that lists out some of the best designs for different situations. I have so many factors. I want to test those in so many runs. What does that design look like? This was one example, and it tells you the confounding pattern and generally the defining relation for it. So then at some point we had a question of how do we compare different designs? What is some criterion that we can use to say, well, in this example here, you chose these design generators. What if I would have chosen something else? What if I would have chosen 4 equals 1, 2, and 5 equals, say, the 1, 2, 3? That is a different experimental design than this one. Which one's better? Are they equivalent? How do we compare those two? And so a very simple way of doing that is with this next concept. So we're going to talk about resolution of our designs. And resolution is a word that is just going to summarize some elements of a screening design. So in a couple minutes, when I say a design is resolution 3 or resolution 4, you'll right away have some general idea of what the confounding pattern is. So let's look at this. Resolution. So how we calculate the resolution of the design is we look at the defining relation. So I equals whatever, and we count how many numbers or how many digits is the shortest one of the terms in that defining relation. So let's go down here. So if we look at this defining relation, we have 3 digits in that term, 3 in that one, 3, and 4. So the shortest term has 3 digits, and therefore it's resolution 3. So we'd say that's a resolution 3 design. Here we have 5 digits. It's a resolution 5 design. 4 is a resolution 4 design. So that's pretty easy to tell, right? And whether it has one term or many term, you're just looking, well, what's the shortest one in the defining relation? And that tells you what the resolution is. So now let's think about confounding patterns. So let's look at this one right here. If I ask you what x2 is confounded with, right? You would say 2 is confounded with, and we're just talking about this one right here. 2 is confounded with 1, 4, 1, 2, 3, 5, 3, 6, 1, 3, 7. Right? You multiply 2 by I and you get 2, and then you multiply 2 by each of these terms. Every time you get a 2 squared, it drops out. Remember that? It's sort of a column of minus ones and plus ones, and it gets to the identity vector and drops out. So to generalize this, 2 is a main effect, and it's confounded with this thing, which is what? A two-way interaction, right? This is a four-way interaction, two-way, and three-way. And what are the important ones that we want to keep track of? What are the important effects? Main effects and two-way interactions. So in a resolution 3 design, we would say, we could summarize, and this is true for all resolution 3 designs, main effects confounded with two-way interactions. And if you think about what you're doing here, well, if you're looking for the shortest term, if there's 3 terms in here, then that means when I multiply by one of the main effects of the terms, I'm going to be left with 2 things left, right? So it's going to be main effects confounded with two-way interactions. Okay. So if we go up to resolution 4, a resolution 4 design, main effects are confounded with what? Three-way interactions, right? Could be 4-way or it could be more, but the worst case scenario would be for x2, x3, x4, and x5, right? And they're confounded with 3-way interactions. So when that happens, when we say main effects are confounded with 3-way or 4-way, those higher order interactions, we simply shorthand that. We say the main effects are clear. That means they're clear of other main effects and they're clear of two-way interactions. So that means the main effects are confounded with unimportant things. What about the two-way interactions? What are they confounded with? In general, worst case scenario for resolution 4. With other two-way interactions, right? So here we'd have 2, 3 is confounded with 4, 5. 2, 4 is confounded with 3, 5, and so forth. So the two-way interactions, they're not clear, they're confounded with each other. That summarizes resolution 4. And looking at resolution 5 design, main effects are confounded with what? 4-way interactions. Great. Main effects are clear. Two-way interactions confounded with 3-way. So they're clear as well. So resolution 5 is really nice. Both the two types of things we're interested in, main effects and two-way interactions, are clear. There are other design resolutions. There's a resolution 2 design. For resolution 2 design, main effects are confounded with what? Other main effects, right? So that's not so good. I've never seen anyone use a resolution 2 design. Not saying you couldn't if you had a whole lot of factors and you were going to do further runs, but I've never seen anyone do it. They generally aren't done. And you can get higher than resolution 5 design, and there are resolution 6 and 7 and so forth. But these, in the main, are the different resolutions that you'll be dealing with. So that's summarized here. We just talked about that business. Not that. And we did talk about this as well. The other statements here, I'll just go over quickly, is remember what was called the projection property of these fractional factorial designs, which means if you do a design and you have a lot of factors, if you throw out a number of factors, then whatever's left, you might be left with a full factorial in the important things that are left. And so this is probably, that's a bit more detail than you need of that. Just remember that projection property. Remember, and also remember we're doing this three-stage experimental campaign. Stage 1 is screening, stage 2 is full factorial. You can get lucky and do your screening design, throw out unimportant factors, and then the full factorial stage is also completed as well. Happens quite frequently. So that's a strong argument for these types of designs. This is really cool stuff that I thought was really neat, and I got excited about it, and I put it in the notes, and I taught a graduate class at UND on this, and nobody really understood it, and so I'm not going to go over it, but it really is neat stuff. This is a detail of how you can tell if you're going to get a full factorial when you drop factors and that kind of stuff, but I got the clear message that it was too much, so let's jump over that, but I kept it in the notes for your reference because it is neat stuff for the interested student, I'll say. All right, let's do this group problem. Go ahead, talk with other people. It's been a while since we've met. before you start part A, you might ask yourself, what fraction of a factorial is it? And your confounding is going to happen in groups of how many? That may help what you do in part A. Did you ever get that stuff for part A? Okay. So for part A, some people may have just gotten the first two terms, and that's why I asked you to, before you do that, think about this. It's a quarter fractional factorial design, so we have two design generators, right? So we have 16 runs, 6 factors and 16 runs, generally takes 64. We're only doing a quarter of them. So that tells you, okay, I'm only doing a quarter of the full factorial runs, so my confounding has to happen in groups of 4, right? So we have a mean and 63 effects that are still there, crammed into 16 runs. So because I have confounding happening in groups of 4, I better have 4 terms in my defining relation, counting the I term. And so the first 2 I think are pretty straightforward. You get those from the defining relations. And then the second term, you multiply those 2 things together to get the third term. So remember that detail? Good. So, yeah, John.
Could you explain the fraction
The fraction in groups. Okay, good question. So we have, so a 2 to the 6th design would be 64 runs, right? So that means I can calculate a mean, and there are 63 other things, 6 main effects, a whole lot of two-way interactions. So we calculate 64 things, but we only ran 16 runs, right? So we have 16 columns, and that means we have each of these has to hold 4 effects in order for those 64 to fit into those 64 effects to fit into the 16 runs. Okay, and that's what helps you determine how many terms you need in the defining relation. So I think on probably an old exam, I think I had a 1/8 fractional factorial design, and there it's a bit of a challenge to make sure that you've multiplied things together in groups of 2 and 3 and so forth to make sure you've got all of the, in that case, 8 terms.
You would never do that to us.
Oh, probably. So, all right. So, what's the defining relation? Everyone okay with the defining relation? Good. Then this part drops out. So, x2, 2 is going to be 1, 3, 4, 5, 3, 4, 6, 1, 2, 5, 6. If I did that right. And 5, 6 interaction. 1, 2, 3, 4, 5 drops out 6. 2, 3, 4, 5, and 1. Does that look right? Looks right to me.
So if you did the 1, would it include the 5, 6?
Yeah, if I would have asked this question, if I would have said, what's x1 confounded with? You're just going to get that. You're going to get 5, 6, all that. What's the resolution of the design? Some people say, who votes 3? Who votes 4? 5 or 6? Resolution 3. And that's, again, the shortest term in the defining relation is that guy right there. That's what determines the resolution in this case, is 3. So you'd see this as 2 to the 6 minus 2, and then a Roman numeral 3. Actually, in the homework coming up, that's how these designs are referred to, and very often. So that tells you a lot of information. It tells me it's a 1/4 design. I need 2 design generators. It's resolution 3. And when you see resolution 3, you can immediately summarize main effects are confounded with 2-way interactions. Okay, so now someone proposed a different design. How are you going to compare them? I'll just give you a minute to make sure you guys all get to that point. Who thinks this is a better design? Most people. Why? Good, higher resolution. So, great. So we said I equals 1, 2, 3, 5 from that one. 2, 3, 4, 6, and 1, 4, 5, 6. So all those terms say it's a resolution 4 design. So it's a 2 to the 6 minus 2, it's resolution 4. And then it's a higher resolution, right? So we still have confounding happening in groups of 4. But why is this resolution better than the other one? Why is this experiment better? So higher resolution, that's the high level answer. Now tell me more detail. Why is this design better? Matt. Good. So in the first one, the main effects are confounded with two-way interactions. In this one, the main effects are confounded with the three-way interactions or the higher order interactions, or you could say main effects are clear. Two-way interactions are confounded with, right, with each other, with other two-way interactions. So if we think about how, that means a higher resolution design is going to be easier to interpret. When we calculate an effect and it's clear, we just say, okay, that's due to the main effect or the two-way interaction that it is. If we calculate things that are not clear, so important things confounded together, then we don't really know which one is really doing the work. Is it this guy or this guy that's really contributing to this effect? Maybe it's both. So we would need to do extra runs to figure that out. But keep in mind an important point. You might ask, well, why in the world would you ever run anything lower than a resolution 5 design? Right? So resolution 5 is nice because they're both clear. Well, the point is experiments can be very expensive, and this is just the first stage of your experimental campaign. You're just trying to sort through a whole bunch of factors to get to that small number that are important. So in that case, or in very many cases, you may run a resolution 3 design and try to cut out a bunch of factors right away and then study them further. There's a rule of thumb that says you shouldn't spend more than about 25% of your budget on the screening stage. So not something you have to memorize, but it's in your notes, and I'm sure you'll keep a hold of those notes and use them in your future. Let's look at an example. It's about time we did some of these things. All right. Some published work. Using CO2 to extract oil from peanuts. Sounds fun. And so they're trying to figure out how do we make this process as efficient as possible? How do we get as much oil from this process as possible? So again, at some point, a bunch of operators and engineers and perhaps chemists got together in a room and they said, here are all the things that could be affecting this. And they got this laundry list of stuff, and they came up with these 5 factors are worthy of study. So that's really important work that we just start with. But in the real world, you got to do a lot of work there. You have to come up with some subset of factors you're going to study. So they decided to study these 5 factors in 16 runs. So what kind of fraction is that? Maybe it says it on there. It does. What kind of fractional factorial is it? Well read. It's a 1/2 fractional factorial. So if we were to study all 5 of these guys, it would have been 32 runs. Confounding happens in what? Groups of 2, right. Confounding is going to be in pairs. And now let's look at, it tells you the defining relation. What was the design generator that they used? What you got? Equals A, B, C, D. And then there's this negative sign that we probably need to talk about. But that's the design generator, right? If you think about how did they come up with this design? They said, all right, 16 runs. We're just going to write down the base design, which is a full factorial in 16 runs. Then we're going to crank out all the computation table. And then we're going to assign add factor E to the ABCD interaction. And if you look at it, you say, well, if I take, whoops, well, let's talk about this negative sign first. Why the negative sign is there? Generally, we think of this as a design generator. We assign A to the A, B, C, D column. But what we did here is, remember, we talked about this in this half fractional factorial. You say, I could run these 16 runs or these 16 runs. They're both equivalent. And this is called the principal fraction, the one that has all the plus ones. Well, they're just running the other half that you don't generally see. So the negative sign, don't fret too much about it. It's kind of a detail. It is just sometimes, for very practical reasons, it may be very hard for you to run, say, some runs in this half, so you run experiments in that half. But statistically speaking, you know, everything else is equivalent. You got the same resolution, you've got the same precision of your runs, all those kind of things. So that's just picking which half of the experiments they did. And so that means E, if you take A, B, C, D, you multiply them together, it would have been +1. We got the -1. Does that make sense? And that's how they got that. So that's the design. Notice it's resolution 5, so main effects and two-way interactions are clear. So we calculated yield. Very often, almost always, but very often, when you're doing a screening design, you're not doing replicates. The whole point of this is not to do a lot of experiments at this stage. So we don't have replicates. We can calculate effects. This is exactly like we did before. And our question is, which effects are real? Which effects are not real? Let's say it a different way. So which of these main effects and two-way interactions are really doing something that's discernible from noise? And which ones are just a reflection of the noise that's happening in the experiment? So how would you think, can we calculate the noise in individual measurements? Think about how you do full factorials. What would we need in order to calculate SP? Replicates. We generally need another set of replicates here so we can calculate the variance and pool it together and all that stuff. But we don't have that. So how can we figure this out? Right. So if we had higher order interactions, we could assume their noise and lump those together. And we'll talk a bit about how to do that in a little bit. But that is the other way of doing it, or one way of getting at it. So think about this. We have a set. I've circled too many. Those are the effects. I don't want to add the mean in there. So we have, think about this. I have a group of numbers, and I want to figure out which ones are noise and which ones stand out from noise. What type of probability distribution does white noise have? Normal distribution. So if we figured out if a number for an effect here was not normally distributed, it would not be normally distributed, right? Okay, so that was a big step, but everyone's with me. All right, so if we made a normal probability plot, the noise would just fall out on that line, right? And the not noise things, which is like probably that huge one right there, maybe others, would show up as outliers. So we could either do a normal plot or a half normal plot of the effects and just look for outliers. That's the graphical method. There it is, done in Excel, as I cruelly make you do all the time in homework, just to show you I feel your pain. I do it myself sometimes. So we're all happy about that. So these are the absolute value of effects. Right? These are the z-scores. You plot z-score by the absolute value of effects. So thus, it's a half normal plot. And we draw our line, find two outliers. And the conclusion would be the main effect of B, the main effect of E are doing something. Everything else is just white noise. This only works if you have enough points here to draw a line, right? And so that means the majority of the effects that you have are just going to be noise. And there are only going to be a few outliers. So that's a guiding principle. It's called effect sparsity. And it just says what the words mean is there are only a few effects that are really significant. Most of what we're going to measure is going to be a reflection of the noise. A half-normal plot assumes what? The mean is what? 0, right? That anchors that line at the origin. For effects, that's generally a good assumption. If it's just white noise that's not doing anything, they should have a mean of 0 and be bouncing around 0. So again, half-normal plot is better than a normal plot for this purpose because it anchors that line. In a full normal plot, that line can be difficult to draw sometimes. All right, any questions on that? That's one way of analyzing this set of data. So, but what about, be really careful with these designs, and be especially careful with Minitab output, because this says this point was due to the main effect of B. But it's not just B, right? It's B and what else? It's the effect of B and the effect of the A, C, D, E, really the negative of that effect. Because of that negative sign, not too worried about that negative sign though. But it's the sum total of the main effect and that four-way interaction. And we are just going to assume, and we'll be really safe in this assumption, that that four-way interaction is not doing anything. So we can assign everything that's happening here in this B effect is due to the main effect of B. But be careful, because in a low resolution design where you have, I'll say a resolution 3 design, if you just have a B here, chances are it's confounded with a bunch of two-way interactions. Minitab won't list those. You have to go back and look at your defining relation and add them in yourself as you think through and say, okay, what's happening? And then you have a bit of a muddier choice of, well, was it B? Was it this other two-way interaction here or another two-way interaction here? Is that clear? Does that make sense? Good. Pareto charts, those are nice. And then there's a full normal plot that shows what we found with the half normal plot. Now, we've done screening designs. These are called the fractional factorial screening designs. And I'll just end with one final note and say, if we have two factors, we have 4 runs, 8 runs, 16 runs, 32, 64, 128, and so on. Now, this is great. These fractional factorial designs are great when you can use them, but notice when we get up into the number of factors, here, if we don't want to do an 8-run design, we got to add another 8 runs to get to 16. Here we have to double the design again to get to 32. That's getting to be a pretty big jump. And then this is a big jump. Wouldn't it be nice if there were designs that sort of filled in the gaps between these two? It would be really nice. And so that's what we're going after. But it's not really super nice because there's an additional price to pay for doing a design in those gaps. And that'll have to be your Tuesday cliffhanger. But don't worry, it'll be resolved on Wednesday. See you then.